Okay, so what is standing wave ratio, right? So standing wave ratio is used as a measure of impedance matching of a load to the characteristic impedance of a transmission line carrying radio frequency. When a transmission line is terminated in any load other than a resistance having a magnitude equal to the characteristic impedance of the line, a reflected wave as well as an incident wave is present on the line. Okay, the sum of the incident and reflected wave at each point on the line gives rise to the different RMS voltage values at different point on the line. The ratio of the largest RMS value to the smallest RMS value of the voltage on the line is called the voltage standing wave, VSWR, voltage standing wave ratio. Okay, the largest RMS and the smallest RMS value are measured at different points on the line, separated by a distance equal to the quarter wavelength. And the ratio of the largest RMS current value to the smallest is called the current standing wave ratio, ISWR. Okay, current is I. The VSWR and ISWR are equal. Frequently, SWR is used in place of VSWR and ISWR. Okay, for VSWR, voltage standing wave ratio is a measure of how efficiently, you remember, how efficiently radio frequency power is transmitted from a power source through a transmission line into a load. Okay, for example, from an amplifier through a transmission line to the antenna. So an ideal system is 100% energy is transmitted. It is efficient in that way. 95% I think is the highest percentage that we can achieve in real world, as there are a lot of errors. There are a lot of other resistance obstacles that it needs to go through. That's why 100% is ideal, but it is I won't say impossible, but this is the ideal. 100% of the energy is transmitted, because in any of the energy in the world, there will be some kind of losses. Okay, like for example, our car, the fuel that we pump into our car from the gas station, it is not 100% going towards our kilometer per hour. Okay, the distance we travel, because some of the fuel is lost when we travel, whether it be heat or noise, radiation, and then when we idle in a parking lot or in the traffic light or in the traffic jam, there is the loss of fuel there. So in any machine that has energy consumption, it won't be always 100% efficient. Okay, right. So standing wave ratio, the optimum condition for a transmitting power to a load over a transmission line is one in which the maximum RMS value of voltage and current are equal to the minimum RMS value of voltage and current. The SWR is an indication of how close or how far we are to the optimum condition for transmitting power to the load. Okay, the closer SWR comes to 1 per 1, like we said just now, 100%, the closer the best or optimum condition is realized. So how are we determining the SWR, standing wave ratio? A ratio is set up with the larger quantity taken first. Okay, SWR is equal to VRMS max per VRMS min, as well as equal to current RMS max and current RMS min. Okay, laboratory and field investigations shows that SWR is equal to Z max per Z min, and the SWR being a measure of mismatch between load and line. As with all ratio, The SWR can also be represented as this equation. Okay, SWR is equal to VRMS max per VRMS mean, or current RMS max and current RMS mean, as well as SWR equal to ZL over ZO. This is what we mainly use in question paper. Okay, SWR equal to ZL, Z load, and Z naught. Okay, all right. As seen before, standing wave is a result of an incident and reflected wave. The radio of maximum to minimum voltage on a line is called the voltage standing wave ratio, VSWR, or simply standing wave ratio. In general, it can be computed as VSWR equal to SWR equal to Emax over Emin and equal to Imax over Imin. And for the case of purely resistive load, like we have seen previously, like this, it is still similar, where VSWR is equal to resistance of the load over Z naught, or Z naught over resistance of the load. It is depend whether the load resistance is bigger or less than Z naught. Alright, effect of a mismatch where Z load is not equal to Z naught. The full generator power does not reach load, and the cable dielectric may break down because of the high voltage from the standing wave. Increase the current square resistance, power loss resulting because of the increased current from standing wave, and noise problem increased by mismatch. Okay, and wavelength of cable, the length of the distance of one cycle of an AC wave, or distance that an AC wave travel in the time required for one cycle of that signal. And a wave is measured from a distance between two identical peaks, high point, as you can see, through the lower points in a wave, a repeating pattern of traveling energy like light or sound. So in reflection of coefficient Kr is a factor to be considered when dealing with mismatched load, and transmission line is the reflection of coefficient Kr. This is defined as the reflected voltage divided by the incident voltage, or alternative as a reflected current divided by incident current. Since the optimum condition of the reflected wave goes to 0, the optimum value for Kr is 0. Okay, this is the ratio of reflected voltage incident voltage, called the reflection coefficient, and can be computed as equals to Er over Ei. All of the value here are labeled as follows: Er equal to magnetic of the reflected wave, Ei is magnitude of the incident wave, ZL is the load impedance, and Z0 is the characteristic impedance. Since both SWR and Kr are an indication of how poor a mismatch exists, there should be a relationship between them, and this is how it is represented. SWR equal to Kr plus 1 over 1 minus Kr. It should be possible to express the reflection coefficient in terms of the load resistance and the characteristic impedance, their inequality to each other being the main cause of Kr being other than 0. And this relationship also exists where Kr is equal to Z load impedance minus Z0 over Z0 minus A plus impedance. This bar represents whether it is positive or negative. The answer of Kr will always be positive. Okay.